Now we're going to learn about graphing rational functions. A rational function is a ratio of polynomials, and ratio meaning like a fraction of one polynomial over another polynomial. The domain is very important in these because there's places where this polynomial function, this rational function, is not defined, and it would be whatever makes the denominator equal to 0. And so because it's going to be undefined there can't be a point there. There can't be graph at that space. And so there's certain values for x which will have no graphing in that space. So let's see what happens on this one. The first thing you want to do to get this organized is to factor the top and factor the bottom using any of the factoring methods that we've had in the past. GCF, factoring by grouping, trial and error, unfoiling, whatever method happens to work in this case. And so this one happens to factor into two sets of parentheses, and we'll put in x and x, and then factors of 12, 3, and 4. And you need the bigger one to be positive, the smaller one to be negative, so that when you do the inner and outer product, you will get a positive 1x when you add the inner and outer product. Then on the bottom, we have x and x, factors of 4, and the only way you're going to get the middle term to cancel out, which there is no middle term, is because one was plus and one was minus. And this is the difference of squares pattern, and so you can see the result there. One of the reasons we factor is so that we can see what the bottom looks like in its factored form, because if x squared minus 4, the denominator, is to equal 0, then this whole ratio would be undefined. And so what we do is we look at it in its factored form and say, what would cause either one of these factors to be 0? Because if either one of these factors were 0, then when you multiply the two factors, you'll get a 0. So what makes x minus 2 equal 0 is when x equals positive 2. And what makes x plus 2 equal to 0? Well, that's when x equals negative 2. So these two spaces are going to be undefined in this function, and so that's going to mean there's going to be no graph in those spaces. It's okay for the top, or the numerator, to equal 0, because 0 over some number is 0, and that's just fine. That's not undefined. But to have the bottom equal to 0 is undefined, and that's not a good thing. So we really don't need to set our top factors equal to 0 to find what can't and can't happen with x. So what you have is the domain, and they'll focus a lot on domain in this section. The domain is all real numbers, and so we'll write the real number symbol as long as x does not equal the two things that make the denominator 0, which are 2 and negative 2. Once we have it in factored form, sometimes it's easier to graph from that form because we can find some other information as well. So the first thing we found is our restrictions of what x cannot be. One thing you want to also check for is in this factored form, are there any common factors on top and bottom that could be divided out or canceled out? And there are not, and so that'll be a different situation. We'll handle that on the next example. So as long as there's no factors that can cancel out, you would consider these what we call vertical asymptotes. And so what that means on the graph is that your graph will never touch that vertical line, and it will never touch this vertical line or cross over it in any way. And so we already have that set up on our graph just from looking at what would make the denominator 0. Those are going to be our vertical asymptotes. The next piece of information that would be helpful is if we knew our x-intercepts and our y-intercepts. And x-intercepts happen when y equals 0. And if you think about looking at this fraction, what would cause this rational expression to equal 0 would be if the top were to equal 0. And so if x minus 3 were to equal 0, or x plus 4 were to equal 0, then that would make the numerator equal to 0, and then that would make the whole fraction equal to 0, because 0 on top makes this equal to 0. So we're going to find out what it takes for x minus 3 to equal 0. That would be x equals 3, would be what would happen when x minus 3 has to equal 0. When x plus 4 has to equal 0, subtract 4 from both sides and you get x equals negative 4. So if x were 3 or negative 4, that would cause the top to be 0, which would cause the whole fraction to be 0, and that means that y would be 0. So what that causes is two x-intercepts. One happens at 3, so we'll put it over here, and one happens at negative 4, and those are our x-intercepts. If you wrote those as ordered pairs, you're saying basically x is 3 when y is 0, and x can also be negative 4 when y is 0. And those are those 2 points that we just plotted. Then it would be good to know our y-intercepts. Our y-intercepts happen when x is 0. So if basically we go to the top equation or the factored out equation, whichever one's easier for you, you will put 0 in for x and see what happens. I would suggest, in case you did something wrong in the factoring or whatever, it would be best to go to the original function. So when x is 0, that would make 0 squared plus 0 minus 12 over 0 squared minus 4. So when x is 0, let's see what that makes y equal. The top would equal negative 12, the bottom would equal negative 4, which divides to a positive 3. And so when x is 0, y turns out to be 3. So that's the point 0, 3, which is on the y-axis as it should be. And that's our y-intercept. On the next page, we'll talk about horizontal asymptotes and how you find those. But this particular example, what you're looking for is the leading term, which is the highest power. And this would be the leading term with a leading coefficient of 1, the leading term of the bottom with a coefficient of 1, and the rest of the terms don't really matter for the horizontal asymptote. And what you're looking for horizontal asymptote is the coefficient of the leading term over the coefficient of the leading term. And so if you do 1 over 1, you get 1. And that y equals 1 is a horizontal line, and that is where your horizontal asymptote is. And with all that information, we can kind of sketch what we think the graph is going to look like. And you could always go to your graphing calculator, put in the original function, get some points off the table, or you could plug in your own x values and get y values that match and get more points. But I can show you kind of what, with all these asymptotes, what it's going to have to look like. What's going to happen is it's going to go through this x-intercept, and it's going to get closer and closer to the asymptote but never touch it. And then it's going to come through down here and also get closer and closer to that asymptote but never touch it. And it has to go through that purple point. Then on the other side, it's going to kind of do the same thing. It's going to get closer and closer to the horizontal asymptote and closer to the vertical asymptote but never touch either one. And it looks kind of like that. And then on the other one, it can't ever cross through the horizontal asymptote, so it's going to, the only place it can go is up close to that asymptote and up close to that asymptote, because if it goes down, it would cross this horizontal asymptote, and that wouldn't be good. So we want to go away from the horizontal asymptote, and we have to go up. It's the only place we have to go. And so the graph of this whole rational function looks like those red lines. It's a curve that kind of happens in 3 separate areas. There's a left piece, a middle piece, and a right piece, and that is the entire function. You could graph it on your graphing calculator to check it and make sure it looks generally like that.